Tile textures. At some point, every 3D artist struggles with how to break up repeating patterns. Texture splatting techniques work, but often require complex shading networks and can be time-consuming to make, but simple solutions do exist. V-Ray has the UVW randomizer, Arnold has at least basic control on its triplanar node, but sadly, Redshift completely lacks one. Hey everyone, welcome back to the channel, and today I have a tutorial on random texture tiling for Redshift with OSL, where I'll be showing you how to turn a tile texture like this into this with minimal effort. If you'd like to download these OSL files, there's a link in the description, and if you'd prefer to have the project file and would like to support the channel, please consider becoming a Patreon. Alright, so just a few notes before we start. This approach does not work particularly well with displacement. I'll talk more about that later, but if displacement is absolutely required, I suggest using traditional texture splatting techniques or searching for OSL bitmap randomizers such as Texture No Tile and Random Bitmaps OSL. The reason why I didn't want to use those for myself is that they do not work with the Maya file node. But every OSL randomizer I've seen requires a bitmap lookup, which means you have to have a separate OSL for every texture of your material, and you lose the ability to automatically repath textures and apply color management rules. Unfortunately, Redshift does not support string functions, so you can't query the file name with OSL. It's just more cumbersome to set up, and I wanted a method that you could use the native file node. Couple more things, if you're not using Maya, technically this should work with any Redshift compatible DCC. I can confirm this method does work with Cinema 4D, but if you're trying to use this method with a different renderer such as V-Ray or Arnold, this method doesn't particularly work, and I haven't really figured out why, but I just think it's a lack of support for the technique that I'm going to show you. So this is specific to Redshift as far as I'm aware, and this was built with Maya in mind. Okay, that's the last note. Let's get started. Alright, so inside Maya, I have a very simple scene set up. I have a plane that's 1 square meter, just so we have something of real world scale just to begin with. In the Hypershade, I have a file node, and then I have a Redshift material. So to demonstrate the problem, I actually don't need this Redshift material, and I can instead just simply connect the out color of my file node directly into the surface shader. This will bypass the need for any type of shading. Middle mouse click and drag that onto the plane, and then go up to Redshift IPR. If I zoom in here, we have a nice rock pattern. And if I wanted to repeat this over a landscape, for example, I'll go to my Placement 2D texture node, and then for the repeat UVs, we could do something like 5 by 5. So here you can clearly see the repeating pattern. So instead of using some kind of splat map or lots of combined noises with lots of different offset images, the idea is you can do the same thing with just manipulating the UVs. So to manipulate the UVs, we could use some type of noise. What I started doing is using a Maxon noise, which is a really good node for various noise types. I can connect that directly to the surface shader here. Go into input, and we can crank up the overall scale so we can see that a little bit better. We could do something like 50. And there's various noise types in here, but the one that works the best would be a cell Voronoi. And what this is going to give you is a Voronoi pattern, but instead of having any type of fall off between the center points and the edges, you get just solid cells. So the basic approach here is to use these grayscale values from a noise to drive the rotation, offset, and scale on the UV coordinates. So before we make those connections, let's connect the out color to the surface shader. So we can see our repeated tile pattern again. Then we're going to use those grayscale values to drive the offset on our UV coordinates. Then we're going to go to our Place 2D Texture node and then click this icon 3 times so all of these little bars light up. And this will show all of our input connections. So we can open up the offset and then on the Maxon noise, open up the out color and connect the out color directly to offset U. And then we could do the same thing into offset V as well. And as I did that, you should have seen that these shift. And to have a little bit more control, we can add a remap value node, connect these 2 lines from the output red to output value, and then just connect the output red into input value. And all of these are the same, so it doesn't really matter which one you use, but the convention is just use the first channel. Then in input and output ranges, you can increase the range to something like 2, and then you can play around with this and it's going to offset all of our textures. And then in theory, you could do the same thing for a scale and you could do the same thing for rotation. Now, unfortunately, if I try to connect this directly to rotation right here. Not only are the values incorrect for degrees, we would need to remap those, but if I try to connect that directly to rotate UV, these nodes are going to be regraphed, and it's going to attempt to connect a unit conversion node so the data type is correct. And if we hover over the rotate UV, Maya is looking for a double angle data type. And this is something that we're not really going to be able to do directly. And if we try to render with this unit conversion node, you'll get an error saying that Redshift doesn't really know what to do with that. So we can't use that approach. Another issue with using the Maxo noise is if we zoom in on one of these seams, you can see a seam right there. And then we play around with the offset, you can see that there's a clear edge, a really sharp edge where rocks get cut off. And if your camera is going to be really close, that is a problem that you'd need to figure out how to solve. So it's fine if your camera was further away, but because rotation also doesn't work, I decided to create my own Voronoi noise. All right, so I'll turn off the IPR. Let's go to some empty space down here. So right away, we're just going to type in OSL. We're looking for Redshift OSL shader. And then before we start doing anything at all, we want to name this shader. And right now there's a bug with Redshift, and at least for Maya. If you compile code and then you change the name of the shader, it doesn't work anymore, and you got to like build another one. Your parameters disappear. So hopefully they can solve that. But I would recommend changing the name right now to OSL Distorted Voronoi 3D. And there's two ways to get the code into this shader. By default, there's this use source option here, and then it gives you some source text just to begin with. All this code is saying is you're taking some kind of channel in, and then you have a channel output, and it's basically just a pass through. So it's not very useful. We don't actually need that at all. We can simply delete it. If you're not interested whatsoever in seeing the code, you can change the use source to file, and then you can download the file from GitHub. So in a browser, you can just type in github.com/cgstirk/OSL, or you can just grab the link in the description. And this will take you to a repository that I've set up for some OSL nodes that I've made. Now these were intended for use with Redshift for Maya. Technically, they should compile in other renderers as well, and they do compile in Arnold and V-Ray, but the technique that I'm going to show you later doesn't actually work with those. This is specific for Redshift. But if you're curious just on this node, just by itself, the distorted Voronoi node does work. So you can play around with that in hopefully any renderer, but I've only ever really tested Arnold and V-Ray and Redshift, of course. So if you'd like to download the files, you can click on code and then download zip. I put these in a project folder called OSL, and you can then just search for this file right here. So you can click on the folder icon and then navigate to wherever that folder is. Double click the OSL, and then that will load up the file for you. So if I click open, you'll get all your parameters and you'll see that it has successfully compiled. However, I prefer to use the use source text, so you can start to modify the code as you work on it, or you can tweak different things and then see the results very quickly. So what I would recommend in that case is to go back to GitHub, grab the code here, open up the code, select all of the text here, copy it, and then you can simply paste it in the source text window, or if you do want to do some editing on them. So you could open up these files in something like Notepad, but if you want a more convenient solution, I would recommend downloading VS Code. And VS Code does come with an optional OSL extension, so you can get some basic IntelliSense, which is really useful if you want to start developing your own OSL. It just highlights things, it just makes everything much easier to work with. So you could copy and paste it from here as well. So once it's pasted in, click compile. That'll take a second or two, and then it should compile right there. Now, if it lags out a little bit, just give it a few seconds. It should be pretty quick, but it really just depends on what your computer setup is. Okay, so now we have this node. I'm going to middle mouse click and drag that onto the plane, and then I'm going to go back up to Redshift IPR. So what we've got is basically just a Voronoi pattern, but we also have added noise around the edges. Now this is what I initially set out to do, but as I was building this, I came up with a few other parameters that I think might be useful, especially for things that aren't manipulating the UVs. So I think this is a pretty interesting node to play around with. So right away we have a very Maxon noise-like color selector. So if we select one of these things and just say like red, for example, we'll tint our values. In color 2, we could do something like blue, have a combination of colors there. But for what we need, I just want to be using black and white. There is also a multicolored mode, which will give you a random color value per cell. So there's no real way to control that besides just playing around with the seed, but I kind of just threw in that as like an added thing that might be useful sometime. I'm going to turn that off though. Next we have scale. So scale is just the size of those cells. While I really like Redshift's OSL implementation in terms of the UI, it does look at your min and max settings that I've set up here, and it gives you a slider for it. If you try to do a value that's above whatever the slider max is, which in this case is 10, it's not going to allow you to put that value in. So there's two options. You can either go into the code, modify that yourself, and then you would need to create a brand new OSL for the UI to work properly with it. Or you could create a Redshift user data scaler node, and then you could connect the out into scale and then do whatever value you'd like there, and then it will observe this one and not the slider. That's an option for you. For convenience, I also have under extra control a scale multiplier, so you can go all the way up to 100 because this value just multiplies this one. And if you're working with really small scales, you can get really tiny cell sizes. That option is there just for convenience. I'm going to set that back to 1. I'm going to set this back to 10. I also have a blobby mode. So for this to really make sense, first I need to get rid of all the noise. So if I set that back to 0, we basically just have that cell Voronoi noise. But if we turn blobby on, you can see that we get kind of this weird distortion. And to really see what this is doing, we take our expansion, we pull this down, we get like a very blobby-like or metaball behavior. So this would be really cool if you have some kind of like bacteria or some cells and you want to be able to show that expanding outward. And if you want to see this with noise, it also works with that. So you can increase the noise amount, and that will also apply to this blobby texture. And then as you increase the expansion to the point where the borders are all connected with each other, the noise is still there as well. So on the noise, we can increase that so it's very large scale, or we can decrease it so it's very small. Now the intention is that the noise scale would actually be very small to do blending, but I'll show you that a little bit later. Now if we zoom in on this and you want some more varied noise, you can increase the noise octaves. And as you increase this, you get more iterations of noise along the edges. You can go all the way up to 20 on this and you'll get smaller and smaller patterns of noise. I'm going to set that back to 1 though, zoom back out, and then under noise type, we have simplex, and simplex is very similar to Perlin noise, but it's more efficient. So I don't have Perlin noise implemented, it's just simplex. And then on cell, kind of looks like some kind of digital camo. If you lower the scale down quite a bit and then zoom in, you can see that like kind of looks like some kind of glitchy looking material, which might be useful. And then there's also hash noise. So hash noise is almost going to give you what looks like a gradient, but it's another useful type of noise. I'm going to put this back on simplex though, because this is the one that I started with and I think it has the best results for what we want. There's also the option to manipulate the time. So if we right click on time, create a new expression, we could just grab this attribute, paste that in here, and then set that equal to time multiplied by 10 or something. Then close that off with a semicolon and create. And then if I close that down, slowly scrub through the timeline, you can see that we get kind of an undulating pattern. So that is also implemented. Let me delete that, and you can just leave that on whatever value you like. There's also the option to use world space, which is default, or object space. So this would be useful if you have a specific object and you want to scale that object up and you want the noise to also scale with it. I prefer this to be on world space though, just simply because I created this for landscapes and I wanted to make sure that no matter how I scaled various pieces of that landscape, the noise scale would be consistent over all the geometry, but that option is there as well. Now this is also a 3D noise, so if I grab something like a sphere, scale this up, and then apply the same shader to the sphere, you can see that there's no pinching at the top, so it is 3D. And to show you what the object space does here, if I decrease the scale and then increase the scale of the sphere, the noise will adhere to that object. If I turn that back off, it's still going to be really small, and then I can make the sphere as large as I want, and the noise is always going to be the same scale. So that's that. And next I also have an offset multiplier. So the offset multiplier it almost looks like it's a seed, but if we lower this value considerably, we get really, really small to the point where you can barely even see anything anymore. And then we grab a Redshift color correction node, attach the out color into the input, and the out color into our surface shader, and then we'll lower the gamma down and then increase the contrast. You can kind of see that grid pattern. You get basically a more uniform looking grid. So I thought this was kind of useful, and when I discovered that you could do that, I actually just made a much more simplified node called Grid Noise 2D. So it's only a 2D implemented noise, but it gives you a very simple grid pattern with the edge noise as well. So if you want something more simplistic and you want everything in a straight line, basically, this might be useful for you. Okay, so I'm going to take this back. I'm going to increase the offset multiplier back up to the default settings and then turn off blobby. I'm just going to use the defaults there. And then for the noise scale, I'm going to set that back up so we can see large noise. So these are all the settings that you can use and play around with, and you can get some really, really cool looking results. Like this one here, just by playing around with things like the expansion and the noise scale. This has other use cases besides just what I'm about to show for the UV manipulation. Okay, so next I'm going to turn off the IPR and just close that down. And then we want to use this OSL distorted Voronoi noise and then attach that to a more complicated network. So we can scroll back up to what we had before, and I'm going to remove the Maxon noise here, remove the remap value. And we also need to remove this placement 2D texture because this rotate UV unfortunately doesn't work. Now, just a little bit of trivia here. If you are a Cinema 4D user and you want to use this same node right here, you should be able to use this directly with whatever your file node UV structure is, because that's already in degrees. So I'm going to go ahead and delete this placement 2D texture node. So now if we reattach our shading group with just the file, back to our IPR there, well, we basically have what we started with. It was just the file node and a shading group. So now what we need to do is add another OSL to do our UV placement. So on GitHub, so I also have the UV placement 2D OSL, and grab all of this text here, copy that, and then we're going to create a new one. So type in OSL, grab a new shader, and I'm going to rename this right at the beginning, UV placement 2D, then paste in the code and compile. And with this node, we're going to pull this up and we're going to connect the out UVs. So we don't actually need this shading group. We can just remove that completely. So on the file node, I'm going to open up the UV coordinates. And then on the UV placement here, we can click on this out UV channel and then connect the out UV 0 to the U coordinate and then the out UV 1 to the V coordinate. So just one note, this is just a 2D placement node. There are 3 values here because OSL requires a vector to have 3 values. You can't have a 2 value vector unless there's a way that I'm just not thinking of. But as far as I'm aware, you still have to have 3. But this one is always just set to 0. It's not usable. So we can connect both of these here. And if I turn on the IPR again, you won't see anything that changes. So on the UV placement node, I can now do the same thing that we did before. I can increase the repeat UV or tiling basically to 5 by 5. We get the same type of pattern. But now we also have some extra controls. So we have rotate UV. This can take values from our distorted Voronoi node over here. And then we also have a global scale, which kind of works in the opposite way of your tiling. So as you increase the scale, it actually makes the image bigger. I just thought it would be useful to have an additional way of controlling the tiling. I'll set that back down to 1 though. And next what we need to do is take the pattern that we created with our distorted Voronoi and then attach that to our UV placement node. So on the distorted Voronoi texture, we can scroll down to our out color, open up the output connection on that, and we can connect out color directly into offset. Offset takes 3 channels, and we can use all 3 of the grayscale values from out color. And right away, you can see everything is offset. So right now, this is the same thing that we could do with max on noise, although we do have that edge boundary. So what we really want to do is control the rotation as well. So for that, I'm going to grab a remap value node again, open up the out color, grab the red channel and plug that into input value, and take the out value into rotate UVs, and then we'll say in parentheses degrees. So it's treating these values going in as degrees. So on the remap value, you go to your input and output ranges. For the output minimum, do something like 1, and then for the output max, 360. So what that means is, because our value range is between 0 and 1, those are going to be remapped to between 1 and 360. You could do 0 and 359, or whatever other numbers you want. You'll get some kind of range between that in degrees, and that will drive our rotation. So right away, you could see that now we no longer have the same orientation of our texture. We have got random rotation as well. And then you could also do a remap value here for scale. So we could connect the red channel of the out color into the input value here, and then I can connect the out value into global scale. And what that does is going to randomly scale all of our values between 0 and 1, which is not what we want at all here. We want to do something like 0.75 and 1.25, otherwise you'll get massively different scales. If I increase that a lot, you'll see that we'll get like really minute textures and really large textures too, which you want to have a little bit more control of that. So we do a much more confined range just to add a little bit of variance. So on this remap value, I'll call this one scale. And then on the second one, I'll call that rotation, just so we can keep track of this. So the really cool thing about this is, now if I zoom in on one of these edges, so let's go and try to find an edge here. And then to find an edge, what I'm going to do, I'm going to grab the out color of our Voronoi noise, connect that directly to our surface shader, just so we can see one of these edges. Zoom in on one of these edges. So then I'm going to reconnect the out color of our file to our surface shader. We can see the original texture. And while this might not be really clear, if I go back to the distorted Voronoi texture, and we'll just take our noise scale down to 0. You can see that's what we had before with the max on noise. With just a little bit of noise there, we can really break that texture up. Now, if we increase the noise amount a lot, you can see that this doesn't really work. It kind of adds these circles like cut out into part of the rock here. So the original idea was you'll just take the noise scale down to some really tiny value. You can see how small these points are now. But if we did something like 0.001, that just blends right in. And I mean, if you get really close to it, you might be able to see some kind of issue if you're like super close to it. But I would imagine that you probably are not really going to notice in most cases. So it looks even better if you zoom out and you don't see any of that blending whatsoever. So that's the general idea of what to do. And you can even go smaller than this if you'd like to. And you can, of course, increase the blending amount quite a lot, but then you'll begin to see the tiling again. So I'll put that back down to something like 0.2. And then I think that's a pretty good value for our blending. So if we zoom back out and we wanted to add even more tiles to this, on the OSL UV placement node, I could do something like 15 and 15. And then you will then once again see a little bit of tiling. So then you can come back to the OSL node and then you could play around with the scale. So if you increase the scale, you'll see more of a repetition. If you decrease the scale, you'll see less and less and less repetition. And when we zoom back in, there's no clear pattern anymore. And this works great for your regular maps. So there is one additional thing that I need to show you, and that's how to handle normal maps. So let's create a new file node, grab a texture there, and then we're going to grab just a normal map. And then remember, on your normal map, you always need to change your color space to raw. I don't have my rules set up right now, but you can always do that as well. And this will be our normal map. And then for the normal map, we can take the out UV value and plug those values into our UV coordinate like this, just like we did before. And then here we actually do need to use that redshift material. And we will need to use a redshift bump map in order to connect our normal map to this. So we take the out color into input, and then plug that into bump input. Then the type of map here is going to be a tangent space normal. And then we'll apply this material to our texture. Now we don't have any type of lights going on, so we do need to add something. I'll go to the redshift menu and just add a simple sun and sky. I'll zoom back out here. And this is going to look like nothing has changed at all. We're going to take these nodes out of the way. We don't really want to see those. And then to really make this clear, I'm going to crank this up so it's quite ridiculous. We're going to select this sun, scale that up so we can see that a little bit better. Then rotate this down so we can really see some of the shading on here. And let me zoom in. And what you see is a lot of weird twisting going on. And that is because if you take a normal map and then you start adjusting the UVs, all of the vectors that determine where the light is and what direction you should do highlights and shadows, all of that information also gets rotated with the texture. And what that means is, instead of having shadows only in one direction and highlights in another direction, they're going to be rotated along with the various orientations of the UVs. So you're going to get shadows in every direction and highlights in every direction, and it's not going to make any sense. So the result is visually a very odd looking kind of swirly mess of shadows going every which direction. So to make this a little bit more clear, let me go back to our UV placement node and then maybe just drop this down to 5 and 5 again, just so you can see this a lot larger. We got shadows here, and we got some other shadows going this way. Yet if we look at our light direction, the light is going screen left to screen right. So if I start adjusting this light and start rotating this light around, we've got shadows that don't really make any sense whatsoever. So we got shadows now going this way on some of them, and then they're going other directions on other parts of these rocks. So what we have to do is figure out how each cell is rotated and then run our normal map through an OSL node that counters that rotation. So back on GitHub, there's one last node here called normalrotationfix.osl. Grab all of this code, copy this. So then we're going to create one last OSL node. We don't need this shader, but I'm going to rename this one as well. OSL normal rotation fix. Then we can paste in that code and compile it. And before we plug the normal map into our bump map node, we're going to run it through this OSL normal rotation fix. So we take the out color from our normal map, pull that into the normal input, and then take the output into our input. Now, as soon as we do that and we turn on our IPR, nothing changes whatsoever, because we also need to grab the rotation. So you could either plug the rotation directly from your remapped value, or even directly from your Voronoi if you're not remapping any of those values, and plug that directly into the UV rotation in. But for convenience, I also have the out rotation included in the UV placement 2D OSL. So we can simply grab the out rotation here, plug that in, UV rotation there, and as soon as we do that, the orientation is now correct. So as I rotate this light around, you can see that the shadows are going in the correct direction as we move over. So all the rocks are getting the correct shadow direction. Okay, so next what I'm going to do is add in all of the other materials. I don't need this shading group anymore. I'm just going to take the out color directly into diffuse color here and pull these down a little bit. Grab another file node. This one is going to be for roughness. I can get rid of the placement 2D texture Open up the UV coordinates here. Plug these in. You can open up the out color, drag that directly into reflection roughness. I'll apply the redshift material to the geometry. And then we get all of our maps. So for the BRDF type, if you want something that's more substance-like, you change this to GGX. Everything else though is pretty much fine to leave as it is. Although we did crank up the bump map to make it kind of really obvious to see what was going on, but if we zoom in, that's going to be really, really strong. So I would recommend dropping that down considerably. So that's looking a lot more natural. The last thing is displacement. Now, unfortunately, I can't get displacement to work, but I want to show you the issue, because if anyone is watching this and they have a solution, I'd be very, very interested in knowing how to overcome this. So let's grab one more file node, and then this one is going to be for displacement. I have a rocks displacement texture here. Map displacement. Get rid of that placement node. Then I'm going to open up the UV coordinates there. I'll actually just pull this entire node up, make this connection just a little bit easier to do. Plug these in here. Move this back down. And then I'll plug this into a displacement shader, a redshift displacement shader. Plug the out color into the texture map. It is a height field, that's fine. For the new range, I'm going to do -0.5, +0.5. I don't want the elevation to change at all. And then we can plug this directly into our displacement shader on our shading group. So on the geometry, we can go to redshift, enable tessellation, and then enable displacement. Turn the IPR on. This is going to be very dependent on your computer specs. This actually appears to be going pretty quickly. But if I zoom in on this, you can see that the default settings are way, way too low. So I'm going to increase the max subdivisions to 12. That's going to take a bit longer to render there. So it's really important here to disable the auto bump mapping, because that's going to influence how the displacement looks. And then for the out of frustum tessellation, we can lower that. So it's basically, that means anything that the camera's not looking at, we just set that to 0, and we can limit that too. Just say that is always going to be 0. Should make it render faster, so it's not rendering displacement anywhere else, but we probably get artifacts closer to the camera. But it should render a bit faster, and it will be easier to see what the issue is around border edges. For the minimum edge length, I'm going to set that to 1. We get some very, very spiky geometry here. And then for the maximum height that we're going to use, we could just say something like 0.2. So it's going to lower these clumps in the middle here. And then we get something that's a lot more natural looking displacement, but unfortunately anywhere that there's a boundary between two cells, we get this kind of spiky looking displacement. So what I imagine is happening is because that I'm using a noise to determine where the UVs are placed, that's giving random points that have different heights. That redshift is not looking at the surrounding displacement, it's not averaging them out, it is simply finding different points, and then it's applying the displacement to little tiny specks. So if we go back to our displacement noise here, and we make this a lot larger, something like 0.2, you can see that the displacement is also going to be a lot larger as well, like the noise size is much larger. We get this type of pattern. So somehow the V-Ray UVW randomizer, which is basically what I would like to see in Redshift, it can do the same type of manipulations just on the UVs, and it can blend between the randomized tiles. So this might just be how Redshift is set up, I don't know. Try to reach out on the forums and the Facebook group, but so far I haven't really heard anything from them. Unfortunately, blurring this doesn't seem to be a good option, because blurring even just a little bit is going to start adding those swirls to the texture. I don't really have a good solution, and unfortunately the lower we do the scale, the more spikes that we get on the edges. So there is one way that I could see this working, which would require the camera to always be positioned in areas where you're not looking directly at a seam or you're not close enough to be able to perceive those spikes. But if you have your cells that are large enough, you can still have your randomization over large areas. And then if you need the camera to go close, you'll just need to position your camera in the middle of a cell. And in the middle of the cell, the displacement is fine, but as it gets to the edges, that's where we see the issue. But of course, you could also just disable that noise scale and not even have any noise. You'll just get a hard edge. But if you don't see that hard edge, then it's not really a problem. If you do absolutely need to use displacement, you can have a look for OSL bitmap randomizers. But the one issue is that you have to use OSL bitmap loaders usually embedded in that node. So I think Maya's file node is one of the best I've ever seen in a DCC, with the rules that you can set up for color space, the repathing options that you can do. So if all of your files get disconnected, you can quickly just reattach everything to a brand new folder or go search for where that texture is. And because Redshift's OSL does not implement any of the OSL string functions, it just really makes using those loaders a lot more difficult, a lot more cumbersome to use. So I really want to use the Maya loaders instead of the Redshift ones. So if anyone has a suggestion, please let me know. All right, so thank you so much for watching. This went on for quite a bit longer than I expected, but if you have any questions, please let me know and I'll try to answer them as best as I can. I have only just started getting into OSL and I'm not sure how much I will pursue it because it's one of these little side things that kind of got in the way of the main objective of what I was trying to do. And what often happens, I go on these kind of rabbit hole adventures trying to figure out something, and then I finally do, and then I end up either not using it or I figure out a different solution or something like that. So I thought I'd create this video for anyone who is interested, but I think this distorted Voronoi noise is pretty useful for other things as well. And hopefully I'll use it for other projects as I go forward. So V-Ray is still my render of choice for most situations, but I am trying to learn Redshift because I'm doing a lot more of GPU rendering, even with V-Ray. And I was kind of surprised by the lack of a randomizer, so I thought I would take a stab at trying to develop one, even though that is not really complete without displacement. Anyway, thank you so much for watching, and I'll see you guys next time.